strategies for the production of clean label food ingredient. As you've seen in the previous presentation also and yesterday, we do get to have a lot of different ingredients from different processes, but one of the key challenges is how do we make it completely clean and green. When I say clean and green, that means it has to be cleaner process, no residues, and avoiding all those chemicals and solvents. So the way I'm going to cover is basics about cavitation technology. You all have heard about ultrasonics, some applications, then the mechanism of ultrasonics or cavitation technologies, followed by drawing down some conclusions. So basics, so if you look at cavitation, it's in simple words, formation of cavities. Even you turn on the water, you form cavities, and how do we use that cavitation? And if those cavity formations is happening because of sound pressure, it becomes ultrasonic cavitation. If it is happening because of water dynamics, it becomes hydrodynamic cavitation. So there is always a cavitation is a bigger term, whereas ultrasound is a specific one which causes the cavitation. If you look at the bandwidth for sound frequencies, ultrasonics, anything above 20 kilohertz considered as ultrasonics. Within that, we have divided a range in that. Majority of the processing application falls within 20 kilohertz. Most of the ultrasonic system which you see in a lab, every lab is having one system and involves a 40 kilohertz frequency or so for chemical processes, for extraction, for different analytical chemistry. And within this majority application, what you see only around 20 kilohertz. And we have some extended zone about 20 to 2 megahertz. Above 10 megahertz is all diagnostic applications. And how ultrasound works in a food system is not, it's always increase the power, it will increase the activity. No. It's something like gently ask somebody, can you please do it? Get your work done. Sometimes can you do it? Sometimes work can get done, sometimes doesn't. That's exact same way ultrasound works. It's always positive. There is no cascading approach. If you increase the frequency, you get a better recovery. No, it doesn't work like that. So depending upon the mechanism, whether it's a mechanical effect, because cavities are formed, how the cavities move, accordingly you have different range of different applications for ultrasonics. So if you look at ultrasonic basics, and if you look into publication, there are around 2 specific journals for ultrasound alone. One is ultrasonic sonochemistry, the other one is ultrasonics. One of the key challenges we'll see in the coming slides, we always say, oh, how you are going to scale it up. It's really difficult to scale it up because it is not reported the way it can be scaled up. If you see across all the manuscript, frequency is common. The frequency systems are designed with this specific frequency. You cannot change the frequency. Max to max, you can get a 2 frequency equivalent, but you cannot change the frequency on one given system. Second, what you see maximum is amplitude reported. That's again given amplitude, how it's vibrate, and based on amplitude you calculate the power, ultrasonic intensity, and acoustic energy density. Last 3 parameters are the critical part for doing any of the scale-up operations, how we scale up the processes. And depending upon the temperature, as you can see different amplitudes, and these amplitudes, what you see in literature says 50%, even you'll see in coming slide 50% amplitude or 100% amplitude, but 100% corresponds to a specific power which has to be calculated. The number of different ways of calculation. Simple one is to do calorimetric method, that is MCP delta T, that means you run the system, measure rate of change of temperature, and then you get to the specific heat, you measure energy. And that's all the cavitation, some of the chemical effects are all to do with hydrogen ion concentration and hydroxyl oil concentration. So if you look at ultrasonic system, so I'm pretty sure some of these systems you have seen in the lab or in your different institutions. So majority of ultrasonic system need a media to flow. That's a liquid. That's a probe type or a bath system. Other one is it doesn't need a media. It's just the air which runs through ultrasonics. So probe type, I'm pretty sure you've seen this type of bath system. You have a piezoelectric transducer which is at the bottom, or you have a probe system which goes in liquid, and this is also a flat probe system which can be inserted into any type of vessel, which operates at 400, 600 kilohertz frequency, and multiple clinical biological applications with 96 well probe or which fits a 96 well, 36 well, depending upon your need, and these can be designed by the manufacturer as what you require. So we get a lot of systems get designed, and this is batch type which works up to 10,000 watt sample, or you have industrial scales. So one of the key questions keeps coming in ultrasonic. Oh, there will be some, when you run ultrasonic, see some of the fittings, leaching of metal coming out of the probe into the sample, and all those questions, they do come. We destroyed almost 10 different probes, run extensively those equipment, and amount of titanium, because these probes are made of titanium, amount of titanium coming in the water is still lower than the European standard, what it should be in the water. And that will, if you use it extent, exactly the same thing. You take any vessel, there is always leaching of chromium or so into the food product is coming in because of the vessel. Same thing in soon in Europe there is going to be a restriction of usage of Teflon because of FIFST, because Teflon is used everywhere and FIFST is coming into the food product. It's exactly the same mechanism how it happens. Other application is medium, which is airborne acoustics, which doesn't need water as medium. Majority of this application is on the processing side for drying, A. B, it also helps in degassing of application. You see when you boil protein with biomass, a lot of foam happens to add anti-foaming, when you remove anti-foaming and all those stuff. Rather, this airborne acoustic suppresses that foam, and that works again based on different mechanisms, not exactly as a cavitation. So this particular system, as you can see before, 40 centimeter wide, so it is industrial scale, and these can run 24/7. Any of these probe systems, they can run 24/7. It's not it heats up, it's not and so. So now these are certain other systems. How do we scale up? This is always the question. If you see a probe, you create very good emulsion, you put oil and water, put an ultrasound, you get perfect emulsion. Then you can show it to industry as previous speaker professor was mentioning, and then he said, oh, how are we going to put this probe into different samples? So once you know your batch type, you can have different configurations of multiple probe system flow through, and as you can see, more and more energy can be drawn when you use a continuous system compared to batch mode. Then again, if you have a liquid flowing through a tube, and you can have different arrangement for the probe. So these are multiple cavitators inserted into the system. Similarly, as you can see, different types of experimental setup. And we don't see a lot of industrial application in the literature because there are a lot of industries, they are using ultrasonic in different form and different processes, but for a specific unit operation. The other approach is hybrid, because sometimes one single frequency cannot do the job. For instance, this particular setup was a 220 kHz probe within a bath system of 45 kHz that was done mainly for drying as well as sample treatment and multiple frequencies. Sometimes they do solve multiple problems. As you can see, this is the normal domestic microwave which was modified with Hilscher probe. And this probe, obviously, you cannot put a metal into microwave, but nowadays you can with certain design. But this particular probe is made up of polyethylene ether ketone. That's basically a sort of plastic which is not a metal. So you can use multiple microwave and probe. We lost IP on this one just because there was another French system which was running into a steel vessel, which is food-grade steel vessel, having ultrasonics at the bottom and microwave both into the same tank. So this is a much more efficient system where we use both microwave and ultrasonic system together to improve process efficiency. How and where this can be used, and you would have seen our colleague the other day, she was presenting on plant treatment of microwave ultrasonics. One way to do is to use ultrasound with an enzyme to improve the reaction kinetics, and once we have to inactivate, you put in a microwave to inactivate the enzyme, at the same time it helps in downstream processing. That's the way this can be combined. And this is a system which was again designed in collaboration with another company. There is supercritical fluid extraction. We all know supercritical fluid extraction is good for extracting non-polar compound. But when CO2 is a liquid state, only the pressure which acts on the biomass. But during that phase, if you introduce a ultrasonic system, it will disrupt the metric, improve the processes, processing efficiency. But we have to be very careful that CO2 has to be in a liquid state. And Hilscher unit cannot be used for this purpose, for this sonics material, because the design of probe becomes very important. Something like high pressure processing, we use 600 megapascal, you see the literature says 900 megapascals, but if you go and to see the material is 900 megapascals, after 100 cycles, you have to relook into the vessel design. So these are all some of the complications when it comes to further scale-up operations. So majority of research stops here. Even we have done a lot of work related to that. You have a batch type, 100 gram extraction improved. Same 100 ml, you go to 1 liter, same vessel, you don't get the same picture. Just because energy distribution is different. You often see the comparison between the back system and a probe system. It's something like you're comparing Ferrari with the scooter, and it just depends on how much power energy goes in. So scale-up operations, as in this case, you can see multiple probe systems designed, and if you know it's 5 minutes, it takes treatment time. You control the flow rate passing through this particular vessel in a similar way, flow rate and the volume, and accordingly you can make it in a continuous process. It is always asked whether it's a continuous process or batch process. What we do, we can't make everything continuous. Fermentation takes 18 hours, it will take 18 hours. We can't make it a continuous. What we can do is have multiple vessels to run the continuous business. So another scale-up issue is also probe system, and then this is another example where this system was designed with hydrodynamic cavitation. It is basically how we change the dynamics of water to cause the cavities, and these cavities help in disruption of biomass. As you can see here, this is a biomass, and after running through hydrodynamic cavitator, you get this slurry. That means first and foremost thing for extraction or obtaining any of the extract is to disrupt the biomass. That's what happens. Even if you put a solvent, water, you heat it, reduce the size, particle size. And an example here is the two different types of cavitator. One is venturi effect, that means water is coming with high pressure, you have concentration take place. So you break the water into tiny droplet, which breaks the biomass. This is what is all about the cavities, formation of cavities. All about rotor is static. Either this is static, this moves, or both moves in opposite direction, or there are different number of patents are there related to the cavitator. So that's rotor is static, and as you can see here, HDC 1 pass. I know 1 pass is no unit, something regulator setting 1 or 2. But actual units, avoid writing it because some of those things are related to process design. So 1 pass is only applicable for this machine. Same thing like 20% amplitude is only specific to the machine unless and until we know what was actual power. 20% means nothing. Same way, if we run through 1 pass and then isoelectric precipitation, that's a common method of obtaining protein, you get perfect protein content and you get better recovery, or as you go for 5 passes, you get higher protein content and recovery also improves. So this is not ultrasound alone or cavitation alone improve the processing yield, but also how it will complement the traditional processes. So if you look at now some of the applications, so these are a lot of different applications being looked into ultrasound for protein. Some of our own studies, some are from literature, and then also apart from having the recovery of the ingredient, there is also another way, place where these type of systems are used. Ultrasonics is used mainly to do the treatment of different plants. And just one example, they will see the numerous examples, how you can modulate the functional properties for different applications. It improves solubility, improves water absorption, oil holding. So these are all the rosy pictures. I'll come to the sad part of it later on. So there are different mechanisms, different ways how ultrasonics can be used for improving the product characteristics or improving the recovery speed. So this is an example where ultrasound and enzymatic approach both together, that was given example over here. As you can see, any of those treatment, whether it was enzyme pre-treatment or ultrasound as a pre-treatment, if we mix ultrasound and enzyme together, it improves enzymatic process in 2 ways. One, it disrupts the matrix, and enzyme solution can go into the substrate to improve the reaction. Whereas if you increase the ultrasonic power, it can inactivate enzyme A. Same thing how it helps in fermentation. When we add yeast to any fermentation media, it goes as a clog. When you give ultrasonic, it disperses that yeast to improve the surface biomass. Otherwise, because of cavities, causes the pores on the bacterial cells or microbial cells, helps substrate to go in and substrate to come out. So that all has been well established. What was observed here, there was no significant increase in protein content by using any of these methods. But when it was glucosinolates, and then the significant reduction was observed in glucosinolates. So here protein recovery was not improved, whereas the processing time was reduced. That was the only advantage we had. It's not recovered more protein compared to control method. This is another example again for the pea protein where the recovery was over 80%. And in this case, again, behavior was quite strange. Hydrodynamic cavitation reduced trypsin inhibitor, whereas had no changes in other phytochemicals. So when we are proposing any technology for extraction or improving processing yield, we have to sell it as a package. What happens to other elements? We often don't tell about it. And ultrasonics or cavitation can be used to improve one particular unit operation, but cannot do all the steps. So there has to be how you integrate into existing process line. That's the critical part. Now this is another example where Alaria esculenta is again seaweed. This island is quite Southeast Asia is quite prominent in usage of seaweed. Now Europe has taken a seaweed as a major source for biorefine for different products and ingredients. And in this case, one of the bigger issue is about the heavy metals and iodine. I was quite intrigued in where I come from. We used to have iodized salt because iodine deficiency is there, whereas in Europe there's too much of iodine. In this seaweed, when different technologies with ultrasonics or microwave pre-treatment were carried out, not only for sterilization purpose to remove the background microbiota, but we are able to significantly reduce the iodine level, which allows it for the product application. So, and how this particular unit operations was, how ultrasonics or microwave together was used in this case, was not only for improving the process efficiency, looking at reduction in amino acid, but to characterize the full biorefinery. So if you see the processes, Cavitation is one of the ingredients which is used in different ice creams and different food products. Cavitation and ultrasonics not only for improving the biomass, for reducing iodine level, and then Cavitation, and we do obtain, we say we give about 90%, 90 minutes over the extraction time compared to conventional. Conventional Cavitation is very simple. You take a seaweed, you boil it for a couple of hours, and then what you get is whatever gel is formed. Either you precipitate with alcohol or you just dry it, depending upon the requirement or the purity. So in this case, when sonics is used, you reduce the time. So you improve the process efficiency, and added advantage is you reduce the iodine content in it because cavitation is gone. The residue, whatever is left for protein, is automatically concentrated because seaweeds are not a good source of protein except few. Yeah, at least not Irish moss or is good for obtain protein, but we do obtain a good amount of protein by combining sonics with conventional isoelectric separation. Now coming back to mechanisms, so if you look at ultrasonics, when any sound happens, this is our school level physics, any sound moves in the pressure, yeah? And then you have stable cavitation, that means cavities are formed but cavities are moving. Third one is transient cavitation pressure. That means the cavities are either imploding or exploding. Exploding, that means boom, because of external pressure. Because internal pressure it explodes. Other one is it implodes. When it implodes, you will see a lot of jet formation. So in these cases, if you see here, stable cavitation, nothing happens. Just sound is going on, particle is just moving. The moment you go for stable cavitation, this will agitate the particle. It will move the particle because those bubbles are moving. Third element is when it collapses, it creates jet, and because of that it causes the damage. So if you look into the literature, you will see ultrasound because of microjet, microstreaming and all those things. But main principle is the cavitation and the cavitation pressure has to be measured. That's one of the way of measuring energy. So these pressure and these bubbles can be looked into by using high-speed cameras, how these bubbles are formed, and that changes depending on type of liquid. As you can see from over here, these are different stuff, these are the effects. But the main one is only the cavitation as a microjet, acoustic streaming, that bubble is moving, because of that particle is moving, or microstreaming, bubble decreases in size or increases in high polyphoton or explosion. And this is what exactly what happens because these cavities, either cell ruptures or in this case is a pitting which causes cell to recover. As you can see over here, and this is not very clear, conventional put any solvent, this is normal surface of a biomass. You don't see any of those pitting, whereas in ultrasonic you see some of these pitting. This will be very clear if you see over here. This is a normal surface of a biomass. After ultrasonic you see all these cavities. Because of these cavities, what happens allows solvent to go in, and you will see over here, this is actually red dots are sodium. White you will add it to the substance. And the static one was mainly on the surface, whereas in this case it allows to move in. This was done with EDX to see in how these things are migrating into it. So this shows the cavity formation. That's the single most principle which helps in ultrasound. Rest all normally we can explain everything. You know, we get delayed, the taxi was late or car was late or whatever. But in this case, main principle is cavitation pressure, transient and stable. Now, we have looked into a lot of different technologies. This particular slide is not only applicable for ultrasonic, but almost all the new technologies we come coming about, because we tend to advertise new technology rather than evaluating a new technology. We should be looking into evaluation because every place, ultrasonic doesn't work some places, high pressure works some places, PE works. It's just not trying to fit a technology just to prove that its technology works. So we all know extraction rate improves. What model system versus the real system? That's always a challenge. Functionality and quality, it not only improves the shelf life, have better reduced thermal impact. What nutritional attributes, we all know about it's having a better recovery functionality also. What is really missing is the toxicological aspect. In some cases, certain technology not reported much in ultrasonics, it reduces certain amount. For example, if we give UV treatment and it reduces cholesterol, because cholesterol is converted into dehydroxycholesterol, which is not detected by HPLC, and we say cholesterol is reduced, but it's converted into more toxic form. So that's why processing induced chemical is the critical part, not only for ultrasonic, but across all the techniques. Even when titanium was leaking from the system after having around 20 hours of continuous running, the amount of titanium was less, and titanium dioxide is one of the food colorant which is quite used as a food ingredient for food coloring substance. So this is one of the critical elements when it comes to ultrasonic. So in nutshell, it's a versatile technology and can be used for range of different applications, and in order to improve the process efficiency, we can always combine with the conventional method, as in the case of ultrasonic pre-treatment followed by enzyme, or ultrasonic treatment followed by your isolated point separation when it comes to protein. Impact of macromolecule is quite complex. It's said like protein can get oxidized, but to larger extent it doesn't. Even if you are looking at the oil, it looks like hydrogen iron peroxide or OH is produced, but it does not cause oil oxidation. So their mechanisms are there, minor causes of these influence, where toxicity or processing induced chemicals are the one which has to be looked into rather than looking alone on the application. So now this is actually, I'll take this opportunity to see we're going to have ultrasonics alone in food technology in Dublin in 8th to 10th of June this year. That's in Dublin. This is we used to have ultrasonics conference in Cavitation in Portugal. This 7th edition was last year, and now we decided to go for a food separate one at the same group. Proteoma Society is organizing. This will be in Dublin, and we are more than welcome to attend this particular conference. And thank you for listening.